So, recall projective space Pn. So, this is Pn K. K is algebraically closed field. So, by definition, this is nothing but you take the affine space, take the punctured affine space, 0 is the point, or you just take k n plus 1 and take 0 and then put an equivalence relation that you take 2 points x and x prime in k n plus 1. Then you say that x is equivalent to x prime if there exists a lambda scalar in K non-zero such that x is lambda x prime. So, basically that means that you take the line passing through the origin, you are identifying that line with a point. So, this is same as lines in k n plus 1 passing through origin 0. Right. Now, this space is called projective. This is called projective space. In some sense, this is a very useful object. In one can give I will show you that one can put a Zariski topology on this space, and this is very useful in the sense to do geometry, because this is some kind of we will see that it is a compactification of the affine space, or it is a completion of an affine space. Some sense, okay. It is like in a topology you have seen that S1 is a 1-point compactification of the real line, right. So, this is in that sense, this is some kind of a complete Zariski topology is a very weak topology. So, everything is compact in Zariski topology. So, compactness, but what is called completeness, so or properness. We will talk about those when we do morphism of algebraic varieties. So, this is a proper algebraic variety, or in some sense what is called complete algebraic variety, and it has some good properties. When we do algebraic geometry, we generally want our object to be proper. Most theorems are only for proper algebraic varieties or projective space in particular. So, also you can think about this space as you have a action. So, GM sometime I will write GM as K star, okay. GM means the multiplicative group. So, GM acts on AN plus 1 by diagonal action. So, you take lambda and then take x1, x2, xn or x0, xn plus 1. Then it acts like diagonally. So, that means lambda x0, lambda xn plus 1. Now, what is this PNK? PNK is you consider this space AN plus 1 minus 0. Now, this is GM stable. This is invariant under GM action, right. If you take a non-zero element in AN plus 1, then GM will take send it to this. So, then this is AN plus 1 0 is GM stable. Right. Now, you have a quotient map, right. Whenever you have some group action, you have the orbit orbit map. Some group is acting on some set, then you have a orbit map. So if you call that pi, then Pn is this. You can think as this. That this is a Pn is the orbit space for the GM action on the affine space. This is another way of looking at it. So projective space is an example of a orbit space. Okay, but another way of looking at now the point is that this projective space, as I am saying, I am advertising about this space, that why it is good. So first I should give a topology on it, right? To study any algebraic variety, first one has to give a topology. So what is the topology on this? So topology on Pn or Zariski topology, because we are doing algebraic geometry. So Zariski topology on Pn. See, as you know that when you do topological space, all topology we constructed is coming from somewhere. It's some kind of induced topology, and so we will. So what is the topology we know? We know a topology of the affine space. We'll try to use that. So something should induce from affine. So that's how it is done. Okay. So some commutative algebra. I need to introduce some commutative algebra, graded algebra. So I denote so say kx. Okay. Consider kx naught xn, the polynomial ring. The polynomial ring you can think as a graded ring. So graded ring in the sense that you can write it like k x naught xn, a direct sum of k vector spaces, where what is k x naught xn? This is just the degree d polynomials, degree d homogeneous polynomials. Right. You can write it like this as a direct sum. Any polynomial you can write it as direct sum of homogeneous degree d polynomials. Right. So what is degree of? So if you take a monomial, say x naught to the power m1, x1 to the power m2, xn, mn, then degree of this monomial is nothing but, if you attach a constant also, so c some coefficient, c is in k, this is nothing but summation mi, and we are only considering the positive degrees. So mi's are all greater than 0. We are not considering negative degrees. So so d is always greater than or equal to 0. Integers. So degree of this is you define like this. And now if you take a polynomial f, you can write it as f naught plus f1 uniquely, right? If f is a degree d polynomial, you can write it as f naught plus f1. So this is a direct sum decomposition. f1 is a now homogeneous polynomial means so now k x naught xn d, this is the vector space generated by monomials of degree d. Take the vector space generated by that. Yeah, so I am saying vector space, that's why. So when I say vector space, 0 will be automatically there, because you take difference between two same monomial, then it will 0 will be there. Vector space generated by this. So instead of polynomials, you can take out monomials, because after all, any homogeneous degree D polynomial is generated by monomial. Okay. So now, so you say now this is a ring. This is not only a ring. This is a graded ring. So this is called graded ring. Graded by this degree D. So now when you say graded ring, so you can talk about graded ideal. So an ideal I in K x naught xn is are not graded ideal, they are homogeneous ideal, sorry, is called homogeneous ideal. If I is generated by any ideal here, it's finitely generated, because these are all Noetherian rings. So there are some generators, and these generators are this F1, F2, Fn are homogeneous polynomial, such that Fi's are homogeneous. Huh? No, need not be same degree. Or equivalently, this is same as saying that if I take any element f in I, then I can write it as f as f naught plus f1 plus f of d, where fi's are homogeneous, right? No, this is some f naught prime f1. So that's why d I have written. In this. And these fi's are also fi's are homogeneous polynomial in I. For all I. So this is another way of saying that. Or in some sense, homogeneous, that means every ideal you can write it as homogeneous sum of homogeneous ideals and sum of homogeneous polynomial, and every such homogeneous polynomial is in I. For example, if you take the ideal generated by x square plus y, this is not a homogeneous ideal, right? But this is a homogeneous ideal, x square comma y. So now, so we want to define what is so topology on Pn. So now if I take any subset here, homogeneous subset of k x naught xn, homogeneous, a subset of a homogeneous polynomial, subset. Finite, because anyway we are interested in ideals, so all are finite. Finite is enough because they will be generator in some sense. So I mean, you can take off infinite, but not required. So you define V of S P in Kn plus 1 or An plus 1 K, such that, or let's write, need not be k, you write Pn plus Pn, such that f of P is 0 for all f belongs to S. Now, first notice that if you have a suppose f is a homogeneous polynomial, just a note that if f is a homogeneous polynomial, f is homogeneous and P is a point in Pn, Fp really does not make any sense, because if f is of degree d, so f of lambda x and f of x, so it will be something like time lambda time degree of f, right? Because f is a homogeneous polynomial, so it will be some sum of monomials of degree d. Now, if I take f of lambda x and f of x, so they are not same if I evaluate. But if f of x is 0, say, then it makes sense. So, zeros of f makes sense. That is if I take a homogeneous polynomial, if at a point if it is 0, then lambda x is f of lambda x is also 0. So, though the function homogeneous polynomial really does not make sense for on a point in as evaluation, but if it goes to 0, then I can talk about this fp equal to 0. So, this is we will see that to define a function we have to take ratio. So, the degree of the functions like f is not a good function. You have to take f by g, where degree of both f and g are homogeneous polynomial and of same degree. Then f by g makes sense. Then f of lambda x by g of lambda x will be lambda power degree f of x by lambda power degree g of x. But since degree of f and degree of g are same, so they will cancel out and it will be fx by g. So, it will make sense. Those are the regular, they will be regular functions. Regular functions are defined like that. But in general, in the affine case, what we saw that if you take just a polynomial, you can evaluate at a point. But here it is not the case. But if you take a polynomial, if it goes to 0, then it makes sense. So that is the reason why we can define this ds. So, this is well defined. Okay, and my notation will be when I take a point, and then this is a notation that when I write like this colon a naught a1 a n, this is a point in the, this is nothing but pi of a naught a n, where pi is the map from your affine space, punctured affine space to your projective space. This is your pi. So, this is a notation when I write colon. Points in projective space will be denoted by this, and point in affine space will be denoted by a naught comma n. So, now proposition. So, these are all exactly like a affine case, some this proposition will hold. So, so this is a proposition. S is a homogeneous subset. Has zero set. Yeah, you can say that it is a algebraic closed subset of Pn. So, we can say this will be our closed subset of Pn basically. So, this is a closed subset. I will define, because to say closed subset, it should satisfy the properties of the intersection of closed is closed, union of closed is closed. So, that is the proposition. Once you do that, then you define these are your closed subset. That gives a topology on Pn. So, suppose S is a homogeneous subset of K x naught n, and since it is now and you take this I generated by S, or you could have started with the homogeneous ideal and take the generator, homogeneous generators, right, with S, whatever. So now so first of all, this is obvious that V of S and V of I, they are same. The generators of the zero set of S and zero set are the ideal generators. So this is obvious. V of 0 ideal, which is also I consider as homogeneous polynomial. This is nothing but P of n k. And V of the unit ideal, this is empty. There is nothing to prove here. Now, if I take S alpha, a collection of homogeneous subsets, then V of union S alpha is nothing but intersection of V S alpha. Standard, just the way in affine case we have seen. And if you take, that means that intersection of closed subset, if I define V of S alpha as my closed subset, that means any intersection of closed subset is a closed subset. The union of S alpha is also a homogeneous homogeneous subset. Each S alpha is homogeneous, so union is also. So for if Ij are homogeneous, ideals of K x naught xn, then V of Ij is V of I intersection Vj. V of Ij is not always is V of I sorry, Ij is not always I intersection j unless they are co-prime. You know that, right? So and yeah. So now, so the proof is exactly similar like affine case. Like in affine case. Try take it as exercise, okay? As your assignment problem. I'll give some assignment problem today, maybe in the next class, sometime. And definition. So now you see this V of A's, they satisfy the topology, the closeness property. So I define this. The Zariski topology on P n K is the topology for which the closed sets are the subsets of the form V of I, where I is a homogeneous ideal. Just take S alpha to be the Product of homogeneous ideal, yes. Yeah. If you take ideal I and J generated by F alpha and G beta, then F alpha, then ideal Ij is generated by F alpha G beta. But if F alpha, that is the definition of Ij. Any element of Ij means that summation A alpha Fg. F is coming from I, G is coming from J.
But we have to prove that those terms are of the form F0 plus F1 plus.
Yes, you can show that. Yeah, that's not a. If you take I and G are homogeneous, Ij will be homogeneous because their generators are basically the product.